Today we're going to be finishing up with talking about balanced trees, in particular AVL trees. You may remember last time we talked about how we can use a rotation to start balancing a tree. And today we're going to finish with rotations by looking at some code for them, and then we're going to show how we can use rotations to go and perform insertions and removals in AVL trees. So just a quick review from last time of what a rotation looks like. Here we have a tree, and we're going to rotate about B. So what's going to happen is D, as you can see, slides down over here, becoming a right child of B, and D is going to adopt C's left children. So if we just show this simulation, you can see what happens. You can also see that several things are going on. First of all, we are making D a right child of B. We are taking C and making it a left child of D. We're also going to have to update parent pointers. So C's got a new parent D, D has a new parent B, and actually B has a new parent as well. It's no longer D, but whatever D's parent was. And also, we're going to have to make B a child of that parent. So if we go and look at the code, you can see that we have the parent now. And what the book does is it passes in to the rotate function the parent of the node that we're going to rotate about. So here you see a right rotate, and what we're really doing is rotating about the left child of node. So node is actually D right here. So if we go ahead and do things, actually what we have is that node points to D, and we are doing a right rotate about B. Now, when you do Lab 11, Dr. Plank is having you do when he passes in a parameter to the rotate function, he's actually passing in as a parameter the node that you're rotating about as opposed to the parent. So that's something you need to be aware of when you write Lab 11. You just can't slap down the code from the book. You're going to have to do some modifications to it. So again, what the code's going to do, it's going to make D be a right child of B. So that's what you see here. Make D a right child of B, and adjust D's parent pointer. 2, D adopts C as its left child. And adjust parent for C. And the final thing, 3, I'll have to do it up here. B becomes a child of P, and adjust B's parent. Okay, so 3 parent pointers getting changed and 3 children getting changed. So what we do, we can now go ahead and run the animation. So I'm going to get rid of this part. And we start. So up here you can see the start, and the first thing we do is notice that node points to D, and we need to get a pointer to C down here. So we do that with left, right child, left, right. Child is the node's left, and then right. So that's what we have here. And we have to save this pointer to C because we will lose it when we make D be B's right child. We'll no longer have this pointer to C. So that's why we're saving this as left, right child. So now we move on and we're checking to see whether the node actually has a parent. Now again, this is handling the special case of a root, which you should not have to deal with in Lab 11 because we're using Sentinel nodes. And remember, Sentinel nodes get rid of these special cases. But here, we're checking to see whether the node has a parent, which it does. So it's not equal to null. And we move down to replace child. And you can see that this replace child, it was replacing the child for node's parent. So the parent of node is P. So if we just, again, draw this. So node parent is P. Then we are replacing node with its node left. So remember, node is the current child, node left is what we're replacing it with. So node left is B, node is D, the parent node is P. So we're replacing D with B, and when we're done, P points to B, and we've adjusted B's parent pointer. I'm not going to go back and look at the code for tree replace child. We did that on Tuesday. Then we move down and we're going to set node left, which again is B. We are going to set its right child to be node. So that's what we clearly want to do. We want to set B to point to D, and this is, if I run the animation, you're going to see another line appear here. And there it is. It just moved, and you see another line now appearing and going from D to C because the next thing we do is set the other child. So by the way, what we did here, this was step 1. So this was doing step 1. This right here was doing step 3. This right here is doing step 2 where D adopts C as its left child. So again, node is D. We're making a left child, and left-right child is C. So that's exactly what we're doing. We're making C be a left child of D right here. And finishing up this animation, everything is done. We're done, and you can see the rotation is complete. Now, the one thing we did not show was this code right here. If D had been a root, so there had been no parent, then when we rotated B up, you can see that B would not have a parent. So we'd first of all need to make the tree's new root B equal, in this case, to B, and we'd want B's parent in this case, because now tree root is B, we'd want its parent to be null. Now again, you should not have to deal with this case in lab 11 because we're dealing with sentinel nodes and it's okay to make B. So what will happen in lab 11 is actually that the sentinel node will be pointing to B, and it's quite all right to make B's parent, in that case, be the sentinel node. Okay, so we won't have to do any special adjustments to our code. We don't have to have a special case in lab 11 for the root. Okay, so we're going to move on now to doing inserts and deletes. So we start by doing an insert exactly like we do into a regular binary search tree. Remember that a AVL tree is a binary search tree. So if we're inserting A here, we start by inserting just using exactly the same insert algorithm we use for a binary search tree. But then, if necessary, we need to rebalance if the resulting binary search tree is not a AVL tree. And in this situation where we've added A, it's no longer a AVL tree. If we do a recomputation of heights, then what we see is when we get to C, the balance factor is +2, meaning that the height of C's left subtree is 2 greater than the height of C's right subtree. And that means we have to do a rebalance operation, and we do it about C's left child B. So you can see the result there where we've rebalanced and B's become the root. So A is added, and you can see they're updating the balance factors. We do our rotation at the first place where the balance factor is greater than 1 or less than -1. So in this case, the first node where the balance factor is greater than 1 is at C. So we go ahead and we do the rebalance, and we do it about B. It's a right rotation. And we update the balance factors. That's the second thing they did here. So the balance factors at that point became updated. You can see there's a 0. B's balance is updated to 0. And D's balance factor, over here, it was unbalanced. It was 2. But with this rotation, the balance factor decreases to 1, which means that D is now in balance. And in fact, what we're going to find out is that we only have to do one rebalancing action. And as soon as we do that one rebalancing action, the entire tree is actually rebalanced, and we should be able to stop at that point. That won't be true with deletes, but it's true with inserts. Now, this case was the easier case. We call it a case where the insert occurred on the outside of the tree as opposed to the inside of the tree. And we're going to refer to this as a zig-zig case. So this is referred to, this case right here is referred to as a zig-zig case. And it's basically an insert on the outside of the tree. Now, not occasionally, but it can just as easily be an insert on the inside of the tree. So let's actually get rid of what I just wrote. So the insert could occur on what we call the inside of the tree. So let's kind of walk through that situation. So we start with this tree and we're going to insert B, and we call this an insert on the inside of the tree, okay, because it's kind of inside. And we did the normal insert. B is less than D, less than C, and greater than A, so it went here. And we updated our balance factors. So 0, 1, and 1 are original balance factors. Here's the new balance factor. So the height of A's left subtree is 0. The height of the right subtree is 1, so the balance factors become -1. So A is still in balance. But when we come up to C, the height of C is 2. The height of its left subtree is 1. The height of A, so it's not shown here, but the height of A, the height of A is equal to 1. So the height of C is 2. The height of its right subtree is 0. I'm sorry, is -1. So the heights differ by 2, making the balance factor a 2 here. And this balance factor is also 2 because the height here is 2. The height in the right subtree is 0. And so the imbalance is 2. But we do our insert, our rebalance at the first node where the imbalance occurs, and the first node where the imbalance occurs is right here. That's the first place where the balance factor is 2. So we're going to rebalance. We're going to try to see if we could rebalance about A, and we're going to see that that's going to fail. So that's the first thing we're going to do here, is going to try to rebalance about A. C is going to come down, B becomes the left child, and we recompute these balance factors, and you see it didn't work. All it did was it kind of changed the imbalance from being kind of this left elbow to being this right elbow. And the balance factor went from being +2 to -2 because the height of A didn't change. If we look at what is the height, so the height of B is 0, the height of C is 1, the height of A is 2, the height of A's left child is -1. So there's an imbalance, but now we say that the balance factor is -2, and the reason it's -2 is we always start with the left, which is -1, so the left height minus the right height is what the balance factor equals. So in this case, the balance factor is equal to -1 minus the right height, which is 1, and we get a -2. Okay? So that gives us a balance factor of -2. Okay, and the reason that the balance factor, so D's balance factor is +2, and that's because if we look at the height of its two subtrees, again, balance factor equals left height minus right height. So that's equal to 2 minus the right height, which is 0, equals 2. And that's why this balance factor is +2. At any rate, this single rotation didn't work. Okay, it left the tree unbalanced. So when we have what is called an inside rotate, or an inside insertion, we need to perform a double rotation. And the double rotation will be performed about the grandchild. So in this case, we start with a rotation about B. So it's the grandchild of the imbalanced node, which in this case is C. and we're going to do 2 rotates about that grandchild. So the first rotate made A left child, and you can see that that brings us to the outside case where it looks like the zig-zag. So now we do a second rotate about B. And as you can see, that nicely rebalances the tree. When we compute our balance factors, B is now in balance, and D's height differs by no more than 1. So the whole tree is rebalanced. Okay? So we call this case a zigzag. So this case is called a zigzag case. And it occurs with an insert on the inside of the tree. Okay, and it's fixed. Okay, the imbalance is fixed with a double rotation about the grandchild not done yet. Well, it's not going to give me more space, so I'm going to have to go up to here. So it's about the grandchild of the first imbalanced node on the path from the inserted node to the root. And the first imbalanced node is one with a balance factor that is either 2 or minus 2. So that's the first node with balance factor equal 2 or minus 2. Okay, and then the way we determine, so you need to determine whether it is a zigzag case or a zigzag case, and the name should help you make that determination. So when we're at the imbalanced node, so here the imbalanced node was C, what we do is we look toward the node that was inserted. So we're looking down toward the node that was inserted. So in this case, we first have to go left, and then to get to that node, we would next go right. So that makes it zigzag. If the direction that we go reverses, it's zigzag. So now I'm going to erase all this to get rid of So now I'm going to go back here, and the imbalance was at C. But now we first went to B, and then we start in the same way down to A. That was twice in the same direction, making it a zigzag. So we're simply looking at whether we go twice in the same direction or if we end up going in opposite directions, making it a zigzag. If we have the zigzag case, we can rebalance with a single rotation about the child of the imbalanced node. If it is a zigzag, it's a double rotation about the grandchild of the imbalanced node, and both times the rotate is about the grandchild. Okay, questions thus far? Any questions about this? Okay. So, in that case, we will look at some code. I'm just trying to get rid of something. You may not be able to see it on my screen, but I'm just trying to, okay. So, let's go and take a look at, well, actually, just to reinforce that, let's look at the 4 possible imbalance cases. Okay, so we're going to start. Here we are. First imbalance case, we insert 12. That is a zig-zig case. Okay, it's left, left. And we would rebalance by rotating about 23. Okay, the second case, we insert 38. It's a zigzag. It's a left-right case. And we do a double rotate about 38. So then the next case, the third possible case, we insert 54. It's an outside case. It's zig-zig. And the final case was we inserted 39. And that was a right-left, so it was a zigzag. So there's 2 outside cases and 2 inside cases. Okay, and then here we're showing how each of those 4 cases is resolved. So with a zig-zag left, we rotate about B, thus obtaining this tree that you see here. With a right-right, it's another zig-zag case. Now it's a left rotate about B, getting that case. Then here it was a left-right situation, so it's a double rotate about C. So first we rotate B about C to get this zig-zag. Then we do a second rotate about C to get the balance. Down here is a right-left. We went right and then left. Again, it's a double rotate about C. We rotate B down to get this zigzag. Then we rotate again about C to balance everything out. Okay? So we're going to look at the insert code now. And you've seen this initial insert code before because it's simply the same code that you use to insert into a binary search tree. I'm not going to go over it now because it's exactly the same code that you saw in Chapter 4 for inserting into a binary search tree. When we're done, node has been inserted. So here we inserted the node, or we passed in the node. When we're done, the node is inserted, but we may have to rebalance the tree. And the rebalancing always starts by looking at the node's parent. The node itself is a leaf. The leaf is balanced. So we don't have to check to see whether the newly inserted node is the root of an AVL tree. By default, or by definition, it is. It's a leaf. And all single node trees are AVL trees. So we're going to start by looking at the parent. And we're going to continue. So we're essentially going to traverse up the tree from the node to the parent. So if all we care about when we have, let's say this was how the rebalancing was done. So let's say that this is the newly inserted node right here. The only nodes that we are going to check to rebalance is this one its parent. Actually, we won't check this one because we know it's balanced. So we're going to start at node's parent. Okay, that's what we're doing right here, is we're starting at node's parent, and we're going to look only at the nodes on the path from the newly inserted node to its parent. And you can see we're doing one node at each level. One node at each level. And since the tree is balanced, that means we're only going to look at order log n nodes for rebalancing. Okay, so we're going to start, and what we do at each of parent node is we look at this tree we call tree rebalance. So we're going to see whether we have to rebalance at that tree. So to look at tree rebalance, we have to go back to the previous section. So here's tree rebalance. So the first thing we do is we update the height of the node. We do that incrementally. This is a very important point. We only recalculate the height for this new node, for this parent node. And then we check the balance factor. So if the balance factor is -2, then we know that the right side is higher than the left side. So if the height, so what we're doing is we're looking at this node. The first thing we did was recompute its height. Okay, so we look at the left subtree and the right subtree, and we recompute its height. And then we recompute the balance factor. Now, if it's -2, what it means is that this right subtree is much greater than the left subtree. Remember, the balance factor equals the left height minus the right height. So if it's -2, it means that the right height must be greater than the left height. So it means in this case that the height, that in some sense, this subtree is higher than the left subtree. So we're going to be rebalancing about in this right subtree. So what we do is we come down and we look, we're going to the right, okay? So we know that the first move is to the right, to this node right here. And what we do is we are going to check the balance. So we call the balance on this right child. Now, we know that this right child is balanced, okay? Because remember that we are rebalancing about the first imbalanced node. So we're rebalancing about the first imbalanced node. So we know that the right subtree, that implies that the right subtree, and in fact, both the left and right subtrees are balanced. So we know that the left and right subtrees are AVL trees, because this is the first unbalanced node. So when we come down to the right subtree, we know that it's an AVL tree. So we check to see if its balance factor is 1. If its balance factor is 1, okay, if it's 1, that means the left height is greater than the right height, which means we have a zigzag case. Okay, so if the We came down here. We checked the balance factor. If the balance factor is 1, we have a zigzag case. Okay, if the balance factor is either 0 or -1, then we have a zigzag case. Now, if the balance factor is 0, it really doesn't matter whether it's zigzag or zigzag, but because zigzag only requires one rotation, we do a zigzag when the balance factor is equal to 0. So if the balance factor is 1, we have a zigzag case. So we need to do a double rotate. That's what the comment here says, double rotation. So we start by doing a right rotate about node right. And remember the book, so the book's rotate is, so remember when the book does a rotate, it passes the parent node and rotates about the parent's child. Okay, so I'm going to get rid of actually all my drawings here. And this is the case effectively that we have here. Okay, this is our zigzag case. So when we call AVLTree rotate on node right, this is node, and this is node right. So when we call AVLTree rotate right here, this is the parent, and this is the node that we're going to be rotating about. Notice that it will be a right rotation. Also notice that this node right here is a grandchild of node. Okay, so this node right here is a grandchild of node. So in fact, we're rotating about the correct node. So when we're done with that rotation, if we label these nodes, so I'll label them as, let's say, A, C, and B. When we're done with that first rotation, what we have now is A points to B, and B's right child is C, and everything else is as it was before. Okay, the other subtrees are the same. So now we return AVLTree rotate left. And we're rotating, so we pass in node A. Remember again, what the actual rotation is about A's child, which is B. And notice B was the grandchild, but the first rotate brought it up to become a child of A. And we're doing now a left rotate about B. So when that's done, we will have that B is the parent of both C and A. And this subtree right here, whatever it is, becomes A's subtree. Okay, so if this subtree was labeled D, then D would now be over here. So that was handled the case of a zigzag. Any questions about that before I move on? No questions? Okay. Now, let's say instead that the situation were that we had A goes to B goes to C, like that. Then, when we came here, again, the balance factor would still be a -2, assuming that this tree right here is the right subtree is greater. Okay, but now let's say that the balance factor down here was either 0 or 1. So that becomes the zig-zag case. And when we look right here, now, since the balance factor is not equal, I'm sorry, balance factor here is -1 because C is where the imbalance is. So that means that remember, balance factor is equal to left height minus right height. C is the greater one, so the height is -1. So if the balance factor is 0 or -1, so if the balance factor was 1, it was a zigzag. But otherwise, no matter what, we do this rotation about B. So if the case is a zigzag, we don't have to do this first rotation about the grandchild. We only have to do the second rotation about B. Remember, if it was a zigzag case, so just going back for a moment, if it was a zigzag case, whoops. If it had been a zigzag case, if this had been the situation, we would do a single rotate. We would have done the rotate, and we would already have moved into this position where we had B and C. That's what this rotate would have done. So no matter what, when we get to this point, whether it's zigzag or zigzag, we're doing the rotate about B, thus obtaining our new balanced tree. Okay, now I'm not going to repeat this for the same situation occurs. It's a mirror case if our situation was either, if our situation instead was something like we had A and we had, well, let's actually now make it B, and this were A and C. And let's say that this tree right here is the deeper tree, and C is smaller, so that the balance factor was equal to 2. Then we would go to this else case, and now we would have the identical things, except we would be just dealing with the left-left case or the left-right case. Okay, this was the zigzag, and this is the zigzag. Okay, I'm not going to go into it because it is very similar. It's just the mirror image of the right-right and right-left cases we just did. So I'm going to let you look at that because I need to move on to delete. But when we're done, then we return the original node. So if we had rebalanced about A, so let's just clear this for a moment. So going back, our situation maybe was A and C and B. When we're done, we have B pointing to C and A. Okay, node still points to A, and that's what we return here. Okay, so at this point, we are done. We have rebalanced about that tree, and it turns out for an insert case, at this point, we know the tree is rebalanced and we could stop here. The book does not. I think maybe for simplicity, we go back and look at the insert case. The book just keeps going. After the rebalance, it just sets the node equal to the node's parent, and it again continues. Now, it is the case, and I'll just write it down, that for insert, once you have found an imbalanced node, and rebalanced it, the entire tree is now balanced, and you can return. I'll prove that next class at the beginning. It's too much time to do it here. But strictly speaking, if it came back in balance, you could actually return at this point. You'd need some indication. Probably AVLTree rebalance would need to return true if it had rebalanced and false if it hadn't. But at any rate, the book continues on its merry way to the parent, even though all future tests of the balance factor will find that it's either 1, 0, or -1. Okay, so I'm about to go on to delete. Before I go on to delete, any questions? Okay, so I'm going to move on to delete. And fortunately, delete is very much like insert. So we've kind of done the heavy lifting now. So take a deep breath. Okay, if need be, stand up and stretch for a moment while I get us set up for removals. Okay, so to start with, delete is very similar to, starts with the exact same delete algorithm that binary search trees start with. So the delete case begins with the exact same delete algorithm used by binary search trees. So just like with the insert case, the delete, you're using exactly the same algorithm that you used with binary search trees. Now remember, okay, so let's just take a look at that. So here we're going to start by first removing 63. Then we're going to remove 84. and then we'll remove 93. Okay, so we delete 63, and as you can see, the tree is now imbalanced. Okay, and in fact, it's imbalanced right at the point where the deletion occurred, at the parent. And hopefully looking at it, in fact, let's ask someone. So if we're at the parent here, what kind of case are we looking at? In fact, let's take a vote right now. So I'm going to take a vote. Are we looking, if it's, what I want you to do is vote. And I want you to vote yes if you think this is a zig-zag case. And I want you to vote no if you think this is a zigzag case. Okay, so please go ahead and make your votes right now. Yes for zigzag, no for zigzag. We're at the parent, and we can see the parent is imbalanced. And very good. So most of you voted and voted for yes. So that is the correct answer. It's a zigzag, and the reason it's a zigzag is that if we look at balance factors, here's a height of 0, a height of 1, height of 2, but the height of its right subtree is 0. Or actually it's minus 1, I'm sorry. The way we're doing it, have been doing it. Actually, the height is 1, 2, and I'm sorry, I'm still not doing this right. It is 0, this is 1, this is 2. The height of its subtree is 0. So we get, I'm sorry, still messing it up. Height of this subtree is minus 1. So the balance factor right here at the parent is 2. So it's imbalanced, and if we look, it's a zig-zag case, so what we're going to do is rebalance about 21. Okay, so clearing this and running it. Balance factor is 2, so we rebalance about 21. Now the balance factor here at 21 is 0. The balance factor here at 84 is also 0 because the height of each of the two trees, 21 and 89, the height of both of them is 1. So the balance factor is 0 and we're rebalanced. So next we're going to delete 84. Okay, now 84, if you remember, and Dr. Planck wants you to, so Dr. Planck, you will find largest key in left subtree. So that's what you'll need to do for Dr. Planck's AVLTree lab. But the book did it the opposite. It finds the smallest key in the right subtree. So just a warning, you can't, again, just blindly copy the book's code, because Dr. Planck wants you to find the largest key in the left subtree, and you have to do it his way because he's using script-based grading. So he expects your tree to look like his tree. So in this case, 84 has 2 children. Because it has 2 children, it's going to find the smallest key in the right subtree and remove it, and that's 89. And since 89 has one child, 93 will become its, will replace it, and 89 will come up to 84. So 93 came up, 84 went in there, or is replaced by 89. Okay, so now we check to see if the tree is balanced. Okay, actually that's not what I want, so I'm going to go back here to 3 and redo it. Okay, at this point it was balanced, because if we look at balance factors, okay, height here is 0, 0. Height here is 1. Height of this is 0. So the balance factor here is equal to left height minus right height equals 1 minus 0 equals 1. So everything is balanced. So after we delete it, 84, the tree was balanced and we didn't have to do any rotation. So sometimes that happens that we don't have to do any rotations. That's obviously the best case. Finally, we're going to delete 93. That results again in an imbalance. So let's just go back because that was kind of fast. So the balance factor was still too fast. Let's let it finish and then redo it. So we delete 93, and the balance factor is now 2 because the height, if we look at the heights, 0, 0, 1. Height over here is minus 1. So again, balance factor equals left height minus right height equals 1 minus a minus 1 equals 2. Okay, so the balance factor is 2. The imbalance is in the left tree. Now the balance factor here is 1, and that means that we can choose the zig-zig case, which is the easier case, and that's what we do. It's only if it was minus 1 that we would have chosen the zigzag. So what we do is continue on with rotating about 21, and we get a new balanced tree. Okay, so the final tree is balanced. So questions about deletion. Okay, let's see, make sure that I don't have any questions. Okay, we don't. So here's the tree removal code, and it is exactly like, so we start, and it has dot, dot, dot here. This is just the same, okay, same delete code as for AVLTree delete. Okay, so not doing anything any differently than what it would be with the normal deletion code. And I actually overdid it. So we get to here, and when we get to the end, node points to deleted node. Actually, we saved, okay, it doesn't point to the deleted node. What we want to do, sorry. What we want to do here, we had saved the parent. Okay, so at this point, parent points to the parent of the deleted node. Okay, and then this is just like insert. If you look at the code, for rebalancing for insert, it looks just like this. It's identical. All we're doing is we're following the node. If this was the deleted node, we're at its parent, and all we're going to do is go up following all the parent pointers. So we're going to do this one, and this one to the root. It's exactly the same as if we had done insertion. So it's very nice. Once we've done the delete, the rebalancing looks just like the rebalancing for the insert operation. Exactly the same. Now the only difference, there's one difference. Okay, remember I said that for insert, you are done after one rebalancing. That's not true for deletes. For deletes, multiple nodes may have to be rebalanced. So you do have to traverse all the way up to the root. Okay, there's a good example in Dr. Planck's notes on that that I'll just point out at the very end. But for deletes, multiple nodes may have to be rebalanced. Okay, so here's another quick example where we first remove 75. So actually, I am going to wrap up. I'm going to let that deletion exercise let you all do that. I just want to say you now have the code you need in order to do Dr. Planck's AVL lab. I definitely encourage you to look at this code from the book and utilize it, but you're going to have to make appropriate adjustments to it. Remember that Dr. Planck's, first of all, it's the lead algorithm. He's looking into the left subtree to find if there's two children for a node that's being deleted. He looks into the left subtree rather than the right subtree. He's using sentinel nodes so that the root is never a null, and neither are the leaf pointers in leaf nodes are not to null but to sentinel nodes, so you have to deal with that issue. He's not keeping track of balance factors, but I certainly think it's fine to keep track of balance factors. Remember that when he does his rotates, he's rotating about a node. So if he's going to rotate about 25, he's going to pass in 25 as his node, but the book will be passing in the parent of 25. So you're going to have to do some adjustments. Okay? Yes, just a sec, I got a question. Okay, Blake, I'll get to where you find the grade strips right at the end, okay? Before, I just want to finish up here, but I'll answer that question. So, I do highly encourage you to also look at Dr. Planck's examples. He has a whole bunch of examples where he both inserts into AVL trees and where he deletes from AVL trees. So if you're having some problems, he has a whole bunch of examples where he deletes from AVLTrees. And his very last example, which he leaves for practice, and actually I'll have you work through it next Tuesday, is in fact an example where you have to rebalance at two different nodes rather than just at one node. That one rebalancing doesn't work. You actually have to rebalance at two different nodes. So I highly encourage you to look at his notes because it gives a lot of highly useful examples, and I guarantee you that on the final, I will make you do this kind of rebalancing operation. I also have some rebalancing exercises. If you look here in April 14th and 16th, you click on the rebalancing exercises. These are from a past test. Okay, so these two questions are from past tests. I highly recommend you look at these as well. There's no after class exercise today, so don't worry about that. As I said, I'll go through a couple things with AVLTrees on Tuesday. I'll look at their running times very quickly to show you why they're guaranteed. Their find, insert, and deletes are all guaranteed to run in log n time. And I'll also go through that Xerxes deletion example. And I'll also prove quickly why, when you have done a rebalance in the insert case, you can immediately return rather than having to go all the way to the root. Now, I had one question about where you find the grade scripts for Lab 10. So I'm going to go back to the labs. And the grade scripts are in Dr. Planck's directory. So grade scripts are, the only time the grade scripts were in my directory were for Candy Crush. Otherwise, the grade scripts are where you always find them in Dr. Planck's Lab A directory with grade scripts. So the standard place. Don't look in my lab directory for the grade scripts. Look in Dr. Planck's Lab A. Does that answer the question, Blake? Okay. Blake's not answering, but I assume that answers the question. At this point, I'm going to let everyone go. So feel free to go.